Every year, thousands of quarries around the world grind through millions of tons of rock. To understand the scale, the largest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. But here's the thing. It's not the machine itself, it's the teeth. Parts weighing up to 150 pounds that bite into granite every single day. How does ordinary steel transform into nearly impenetrable armor? And what's hidden in a process only engineers get to see? Stick around till the end, and you'll discover the secret an entire industry depends on. To grasp the scale, the biggest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. Its bucket could hold 2 Greyhound buses side by side. And each tooth on that bucket wasn't some small thing, but a work of engineering art, weighing 50 to 150 pounds, able to bite into granite rock day after day without wearing down. Let's start with the fact that these teeth are made using 2 main methods, casting and forging. What we're seeing now is casting, where the toughest parts for the mining industry are born. Some manufacturers choose high carbon steel with carbon content from 0.33 to 0.5%. But here's where it gets really interesting. Heat treatment that turns ordinary steel into nearly impenetrable armor. Right now, we're standing next to an electric arc furnace. This thing melts steel at temperatures over 2,700 degrees Fahrenheit. That's so hot it could melt an aluminum can in 1 second. Here the steel gets purified from impurities, then it's mixed in an argon-oxygen deoxidizer. This process keeps the gas content in the steel extremely low, which is critical for the strength of the future teeth. Once the steel is ready, the casting magic begins. There are several methods: sand casting, precision casting, and forge casting. The most interesting one is precision casting, also known as lost wax. Check out how this works. First, they create a wax pattern of the future tooth. This isn't just any part. Each tooth has a complex shape, with a sharp tip and a solid base for mounting. The wax pattern is manufactured with accuracy down to a few thousandths of an inch. Then, these wax models are assembled onto a tree, a special structure that can hold anywhere from 5 to 10 teeth at once. Next comes the coolest part. This tree gets dipped into a ceramic slurry again and again, building up layers like an onion. Each layer needs to dry and harden. They repeat this process 7 to 10 times until they've built up a shell about half an inch thick. This ceramic mold can withstand the temperature of molten steel, 2,800 degrees Fahrenheit. Then the wax gets burned out, literally. They heat the mold to 1,500 degrees, and the wax melts away, leaving behind a hollow cavity in the exact shape of the future tooth. Now this mold is ready to be filled with molten steel. Look at this ladle. It's holding 2,000 pounds of carbon steel glowing bright orange. Maxing out at 2,650 degrees Fahrenheit. One ladle like this can fill 20 to 30 tooth molds at once. The molten metal pours fast, but carefully. Air bubbles can ruin the entire part. After pouring, free cooling begins. This is critically important. The molds cool for 8 to 12 hours down to room temperature. Once everything's cooled, they break the ceramic shell. This is done with special hammers or sandblasting machines. And there they are, cast teeth, still gray, with ceramic remnants. But this is only halfway. The real magic starts now. Heat treatment. The teeth go into a furnace for normalizing. Here they're heated to 1920 to 2070 degrees Fahrenheit and held for 10 hours. This temperature lets the steel recrystallize, refining the grains and making the structure uniform. The metal becomes stronger and more elastic at the same time. After normalization comes the critical step, hardening. The teeth are heated again, this time to 1870 degrees Fahrenheit, then rapidly cooled in oil or water. This process transforms the steel's internal structure into martensite, a super hard crystalline form that can handle enormous loads. But there's a problem. After hardening, the steel becomes brittle, like glass. One strike, and the tooth can crack. That's why the next step is tempering. The teeth are heated again, but this time to a lower temperature, 400 to 450 degrees Fahrenheit. This relieves internal stress and adds toughness, while maintaining surface hardness. The final hardness of bucket teeth for draglines runs from 48 to 52 units. But that's not all. Some manufacturers go with induction hardening, a process where the tooth surface gets heated by electromagnetic induction to temperatures between 2700 and 3000 degrees Fahrenheit in just seconds, then instantly quenched with water. This creates an ultra-hard surface layer about 0.04 to 0.08 inches deep, while the core stays soft and shock resistant. After heat treatment, every tooth goes through quality control. Look, this inspector is using ultrasonic equipment to find internal cracks that are impossible to see. Even a microscopic crack can cause catastrophic failure of the tooth under loads of several tons. They also check the surface hardness with a special device, a hardness tester. It presses a diamond cone into the surface and measures the depth of the impression. Too soft, it'll wear out fast. Too hard, it might crack. Then the teeth are ground and polished. This isn't just about looks. A smooth surface resists abrasive wear better. Rough spots wear faster because stress concentrates there. The final stage, painting and marking. Each tooth gets a unique number that indicates the batch, manufacturing date, and steel characteristics. It's like a passport. If a tooth fails prematurely, you can trace its entire manufacturing history and find the problem. Now for the most interesting part, testing. One tooth from each batch gets sent to destructive testing. It's mounted in a special machine that simulates working conditions in the quarry. The machine pounds the tooth with a hydraulic hammer at 1 million pounds of force, again and again, until it fails. They record the number of cycles to failure. A quality tooth survives over 50,000 impacts. They also run an abrasive wear test. The tooth gets dumped into a drum with granite gravel and rotated thousands of times, simulating months of work in the quarry. Then they weigh it. The weight loss shows how much the tooth has worn down. The best teeth lose less than 0.5% of their weight after the equivalent of 1,000 hours of operation. Let's talk numbers. One large dragline has a bucket capacity ranging from 110 to 160 cubic yards. A single bucket can have anywhere from 40 to 60 teeth. Each tooth weighs between 50 and 150 pounds. And these teeth need replacing every 3 to 6 months depending on how hard the rock is. Picture this. One dragline can burn through 80 to 120 teeth a year. And there are machines like this working all over the world. The US alone has about 50 big draglines operating in coal mines. That means tens of thousands of these teeth get manufactured every single year. The cost of one tooth? Anywhere from $1,000 to $3,000 depending on size. And a subscription to my channel costs just 2 teeth. Just kidding. It's completely free, so I'm expecting those clicks on the subscribe button. Now multiply that by 60 teeth on a bucket. That's $180,000 just on wear parts. And you've got to swap them out twice a year. That's why every single tooth has to be perfect. The economics of the entire mining industry depends on the reliability of these steel fangs. Every year, the world burns through over 100 billion gallons of fuel. But nearly half the energy for the east coast of the United States flows through a single steel artery stretching over 5,000 miles. Colonial Pipeline, a tube just 3 feet wide that pumps more than 100 million gallons of gasoline, diesel, and jet fuel every single day. Without it, gas stations shut down, prices skyrocket, and panic sets in. In 2021, one cyber attack nearly paralyzed half the country. How does this silent system actually work? What's hidden inside that dark pipe, where pigs weighing hundreds of pounds roam free? And what's the weak link that could change everything? Stick around till the end. You'll see the invisible machine that fires up millions of engines every day. Today, we're standing next to one of the most invisible, but absolutely critical pieces of infrastructure in the United States. A system without which millions of cars simply wouldn't move. What you're looking at is the Colonial Pipeline, a massive fuel artery that pumps energy every single day to half the country. It's not a factory, not an oil rig, not a port. It's a pipe. Steel, buried underground, silent. But it's what keeps modern life moving. A metal cylinder, roughly 3 feet across. The total length of this system? Over 5,000 miles. That's farther than the entire width of the continent. And inside this pipe, millions of gallons of gasoline, diesel, and jet fuel flow every single day. The coolest part is when you learn there aren't separate pipes for each type of fuel. Everything goes through the same route. Regular, premium, diesel, jet fuel, all moving down the same steel highway. But not mixed together. They travel in batches, one after another. First, say, a batch of regular gasoline. Behind it, a batch of premium. Then, diesel. Between them are thin transition zones where the fuels mix a little. These zones are carefully tracked and then separated at terminals, so not a single drop ends up where it shouldn't. To keep this flow moving, you need force. And that's where pumping stations enter the game. Along the pipe route sit dozens of powerful complexes. Each one looks like a small industrial yard with tanks, electric motors, pipes, and control panels. Inside, pumps capable of creating pressure in the hundreds of pounds per square inch. Now, one of the coolest parts of this whole story. Inside the pipe, they regularly launch a special device the industry calls a pig. It's a big metal cylinder with rubber or polyurethane rings around the edges. Its diameter almost perfectly matches the inside diameter of the pipe. They insert the pig into a special launch chamber, close the hatch, and the fuel flow literally pushes it forward. Inside that dark pipe, this device travels hundreds of miles, pressed against the walls. It scrapes off paraffin deposits, rust, micro debris, and modern versions even scan the metal, searching for cracks and weak spots. Some of these pigs weigh hundreds of pounds and are packed with electronics like a small underwater drone. They collect terabytes of data about the pipe's condition. Then they're caught in a receiving chamber at the other end of the route, and the information gets analyzed. Now let's look at what a typical fuel journey looks like. A refinery ships a batch of gasoline into the system. It enters the pipe under high pressure. Then begins a slow but continuous journey. Flow speed, a few miles per hour. That sounds slow, but consider this. The pipe runs 24/7, no breaks. After a few days, that same batch reaches a distribution terminal. There it's received into massive storage tanks. Additives are mixed in, composition gets adjusted, and then it's shipped by tanker trucks to gas stations. The driver filling up your car almost never sees the actual pipeline. But that pipeline is what delivered the fuel to his tanker. The whole system is built around risk management. Pressure sensors, leak detectors, temperature gauges, all stationed along the route. If an anomaly pops up anywhere, automation can shut down that segment in seconds. Valves slam shut. Flow stops. Problem contained. Now here's the big question. What happens if this pipeline stops for even one day? Answer: domino effect. Gas stations start running dry. Prices spike. Tanker trucks pile up in lines. Airlines scramble for alternative supplies. Businesses count their losses. All because somewhere underground, a steel artery stopped pumping. This has happened before. And every time, it becomes clear. Colonial Pipeline isn't just infrastructure. It's the hidden backbone of the economy. You don't see it every day. You don't snap photos of it for social media. But every time you turn that key in the ignition, somewhere hundreds of miles away, buried underground, a system has already been working to make that moment possible. And that's exactly why places like this deserve to be talked about. Because behind that ordinary gas pump nozzle at the station stands one of the largest engineering structures on the planet. When it comes to the scale of Colonial Pipeline, the numbers look almost unreal. Every single day, over 100 million gallons of fuel flow through this system. That means in 24 hours, this pipeline can fuel tens of millions of cars, thousands of trucks, and hundreds of planes. Roughly 45% of all the fuel consumed by the East Coast passes through this very network. The entire system stretches over 5,000 miles, with more than 50 pumping stations. Each one pushes tens of thousands of gallons per minute, keeping the liquid flowing non-stop. If even one major section drops out of the chain, supply volumes plummet by millions of gallons a day. The system serves more than 200 terminals across different states, from the Gulf Coast all the way to New Jersey. From there, fuel gets hauled out by roughly 20,000 tanker trucks every single day. Basically, every other gas station on the East Coast depends on this route in one way or another. One of the clearest examples of just how vulnerable America's fuel system is happened in 2021, when a cyber attack shut down Colonial Pipeline. Seemed like a temporary technical glitch, but the impact hit almost instantly. In less than a week, the scene at gas stations started looking like a crisis scenario. In North Carolina, over 70% of gas stations ran dry. In Georgia, nearly half the pumps sat empty. People waited in line for hours, hoarding gasoline in jerry cans, and social media flooded with videos of empty stations. Prices reacted just as fast. The cost per gallon jumped by several dozen cents in just a few days, meaning millions of drivers faced extra costs every single day. And businesses scrambled to rethink their logistics. This incident showed exactly how one shutdown of a major pipeline can flip a stable fuel market into a zone of panic and shortages in a matter of days. By the way, my body's running low on your subscriptions. According to economists, every day a system like this sits idle costs the economy hundreds of millions of dollars. Trucking companies lose out. Airlines lose out. Delivery services, all of them take a hit. A single day of downtime can delay the shipment of tens of thousands of tons of goods. Safety deserves its own conversation. Every year, hundreds of millions of dollars go into monitoring and upgrades. Along the route, thousands of pressure and leak sensors are at work. They check the pipe's condition every few seconds. In a year, the system processes billions of measurements to catch even the smallest anomalies. The pipeline also gets regular inspections using smart pig devices. In a single run, one of these tools can scan hundreds of miles of steel and detect cracks just a few millimeters wide. Thanks to that, over 90% of potential failures get fixed before they become a problem. From a financial standpoint, Colonial Pipeline is infrastructure with billions of dollars in turnover per year. The company serves hundreds of clients, from major oil traders to regional distributors. Tens of billions of dollars worth of fuel flows through the system annually. Every year, the world produces over 1,800,000,000 tons of steel. That's enough to build thousands of bridges, but only one of them will become North America's longest cable-stayed bridge, the Gordie Howe International Bridge. 125,000 tons of metal, over 1 million bolts, and a span of nearly 3,000 feet with not a single support in the water. How do two countries stitch steel together over a river? And what happens if even 1 millimeter goes wrong? Stick around to the end, and you'll see the moment when American and Canadian metal literally kiss in the sky. The birth of the steel backbone for the Gordie Howe Bridge starts long before the first beam reaches the construction site. This is a cross-border industrial operation where the Canam Group plays the starring role. The steel for this project isn't just metal. It's the result of collaboration between American and Canadian steel giants. Sheets of high-strength specialty steel are forged at mills in both countries. Then massive rail cars funnel them towards specialized fabrication shops. When you walk into a Canam plant, the first thing that hits you is how modern robotics tames raw matter. You won't see blacksmiths with hammers here. Laser systems and giant computer-controlled machines rule this space. Steel plates several inches thick are cut by laser or plasma with precision down to tenths of an inch. That's critical because each edge girder is made up of dozens of elements that must fit together perfectly during welding. The most dramatic moment at the plant? Assembling that famous box girder beam. Massive magnetic cranes hoist steel plates 49 feet long and position them into specialized assembly jigs. Here begins a process engineers call submerged arc welding. It's an automated technique where the welding head travels along the seam, hidden beneath a layer of special powder, flux. This prevents metal spatter and ensures perfect joint quality. Inside, the beam is reinforced with countless stiffener ribs. These are vertical steel partitions that prevent the structure from deforming under the colossal weight of the roadway. Every weld passes through the hands of inspectors armed with ultrasonic and X-ray flaw detectors. On the Gordie Howe Bridge, there's no room for average quality. If they find even a microscopic air bubble inside the metal, the part gets rejected. After welding, the finished beam heads to the shot blasting chamber, where its surface gets cleaned to a shine, then receives multiple layers of special polymer coating. This is armor against moisture and salt, designed to protect the steel for 100 years. Folks, check this out. I'm standing at a safe distance right now, but even from here, this thing looks completely unreal. We're used to the word beam, but on the Gordie Howe International Bridge project, that term takes on a whole new meaning. Each of these edge girders is a 100-ton steel titan that's literally twice my height. I've watched them get moved. It's a full-on special operation. Giant multi-axle platforms creep slowly across the construction site, and the gravel literally buckles beneath them. When they lift one of these beams into the air, it blocks out the sky. That's the moment you realize there's nothing impossible in this world for someone who's learned to tame steel at this scale. This is pure, raw, 100-ton power that's about to become part of the longest cable-stayed bridge in North America. Ever build with Legos as a kid? Now imagine one piece weighs 100 tons, and instead of plastic connectors, you've got a blazing welding arc. We're on the banks of the Detroit River, and what you see behind me, engineers call an assembly node, but I'm calling it a playground for giants. The assembly process for the Gordie Howe International Bridge means building giant modules right here, on the ground. You can't just hoist one beam and clip it together in the sky. First, on special steel jigs along the shore, these 100-ton edge girders get welded into single sections. It looks incredible. Two parallel edge beams connected by cross-steel trusses, forming a massive frame. When a section's complete, it resembles part of an aircraft carrier deck that someone decided to build in the middle of an industrial zone. Why do they do this on shore? Because here, welders have something they don't have at 492 feet up: stability. Every seam, every joint has to be perfect. I walked up to these guys. They're working in special masks with fresh air supply, because the welding intensity here is so high that the air around them literally burns up. You see these welds? They're as wide as my palm. Robotic welders pass dozens of times over the exact same spot, laying down layer after layer to create a monolithic joint that no storm will ever tear apart. Now look at these bolted connections. Where welding can't be used, thousands of high-strength bolts take over. Each one is tightened with such force that the steel plates start working as a single unit through friction force. When a section like this is fully assembled, they check it with laser scanners. Accuracy has to be within an inch. If there's even a hair's width of misalignment, literally the thickness of a matchstick, then midway across the river, when the Canadian side meets the American side, they just won't line up. The feeling of being next to one of these sections? Pure adrenaline. You're standing inside a steel box that's about to hang over a gorge, carrying thousands of people. The sound here is something else. Constant grinding of metal, hissing of pneumatic tools, and the rumble of heavy cranes. Across the water, slow and almost silent, a massive barge glides forward. Resting on its deck is the very section we saw on shore. A steel frame with edge girders weighing hundreds of tons. From the bank, it looks like a surreal steel island drifting between two countries. But the moment that barge locks into position directly beneath the bridge span, the air gets electric. You look up, and 150 feet above the water, you see the red jaws. Special lifting devices mounted on the edges of the completed spans. What engineers call the heavy lift is beginning. This isn't a quick process. When the winches start working, the steel cables tighten like strings on a giant guitar. You hear that sound? That low, guttural groan of metal accepting colossal weight. The section slowly lifts off the barge. The first few feet of empty space appear between the water and the steel bus. In that moment, all the weight of this monster bears down on the pylons and cables. You literally see the bridge settle a few inches, coming alive under the load. I stood on the shore, holding my breath. Surveyors with laser rangefinders track every millimeter of lift, second by second. And then, when the section finally lines up with the bridge edge, the most critical part begins. The iron workers, who look like tiny dots against the white beams, start catching the section. They use hydraulic jacks to perfectly align the bolt holes. This is the moment when American and Canadian steel has to kiss. When the first pin slides through both plates, a wave of relief you can physically feel washes over the construction site. Its main span is 2,799 feet. That's a massive pile of steel hanging over water with zero support in the river. That makes it the longest cable-stayed bridge in all of North America. Over 125,000 tons of structural steel went into this thing. Constant corrosion from salt water. There's colossal metal vibrations to build 1.5 Kitty Hawk class aircraft carriers. And what about the fasteners? Connecting all these massive beams took over 1 million high-strength bolts. Each bolt is a tiny guarantee that this backbone will handle 100 years of use and more than 2.5 million trucks every single year. It's a genuine metal ocean, tamed by human ingenuity. Did you enjoy this journey from cutting up aircraft carriers in Texas to the birth of new titans in Detroit? If so, you know what to do. Hit that steel bell, smash the like button, and make sure to subscribe to the channel. There's a metal so rare that humanity mines less of it in an entire year than gold in a single day. A metal that costs $2,000 to $4,000 per pound. A metal you've never heard of, but one that's keeping the plane you flew on for vacation from falling out of the sky right now. This is rhenium, the rarest stable element in Earth's crust. A silvery white metal that doesn't exist as its own ore and is only extracted as a byproduct. Without it, we wouldn't have modern jet engines, and aviation would be stuck at mid-last century levels. Let's dive into the world of the planet's most exclusive mineral, where every gram is worth its weight in gold, and applications are measured not in tons, but in pounds. Let's start with the scale of rarity. Rhenium makes up about 7/10,000ths of a part per million in Earth's crust. For comparison, gold is 4/10,000ths. Platinum is 5/10,000ths. But gold and platinum can be found as nuggets or concentrated ores. Rhenium never happens that way. It's scattered as microscopic impurities in other ores, mostly molybdenum and copper. The concentration is so low that even talking about rhenium ore isn't really accurate. It's always ore of something else that just happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's often used as alloys or powder. In nature, rhenium occurs in only one mineral, jacasganite, which is so rare it exists in literally just a few places on the planet and has no commercial value. All industrial rhenium is obtained as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. It's a byproduct of a byproduct. Imagine the scale. To get 1 kilogram of rhenium, you need to process about 200,000 tons of copper ore. 200,000 tons of rock for a kilogram of metal. It's like looking for a needle, not in a haystack, but in a field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the USA, Kazakhstan, and Armenia. Chile dominates about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where copper and molybdenum are extracted, with rhenium obtained as a side benefit. The pit is so massive it's visible from space, about 2.8 miles long, 1.9 miles wide, and over half a mile deep. The rhenium extraction process is complex and multi-staged. First, they mine copper ore and concentrate it through flotation, producing copper concentrate. This concentrate contains molybdenum, which is also concentrated and separated. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically from 0.05 to 0.2%. Still with me? Let's keep going. The molybdenum concentrate gets roasted in special furnaces at temperatures around 2000 degrees Fahrenheit or higher in air. Molybdenum oxidizes to molybdenum trioxide, which can then be reduced to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which at this temperature evaporates and escapes with the gases. The gases pass through a complex system of scrubbers, towers where the gases are washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. The concentration of rhenium in these solutions is minuscule, grams per ounce, but it's something workable. The solution is purified from impurities of molybdenum, copper, lead, and other metals through multi-stage chemical treatment. Then, rhenium is precipitated as a white crystalline powder. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen. Hydrogen reduces the rhenium oxide to metal. The result is rhenium powder, which can then be sintered, melted, or used directly. Every year, humanity produces around 50 tons of rhenium. 50 tons! For comparison, we mine roughly 3,000 tons of gold annually and 20 million tons of copper. Rhenium is so rare that global stockpiles at any given moment are measured in hundreds of tons, not thousands or millions. So here's the question: why bother mining something this scarce? The answer: jet engines. Close to 80% of all rhenium goes into the aviation industry to manufacture superalloys used for making turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 3,000 degrees. Pressure is massive. The blade spins at tens of thousands of revolutions per minute, experiencing loads of hundreds of tons per square inch. Corrosive environment with sulfur impurities from aviation fuel. And all of this for years of continuous operation with zero margin for error. If a blade cracks mid-flight, the engine disintegrates, the plane goes down. Nickel superalloys, the primary material for turbine blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, and titanium. But even these complex alloys couldn't withstand temperatures over several thousand degrees for extended periods. Until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of the superalloy and prevents defects from moving through the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load at temperature. All metals creep, but rhenium slows this process down by several times. Adding just 3% rhenium to a nickel superalloy increases the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much. But in jet engines, every 18 degrees of additional temperature gives roughly 1% increase in efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. These are the so-called second and third generation superalloys. A single turbine blade can contain 5 to 20 grams of rhenium. One Boeing 787 or Airbus A350 engine contains roughly 13 pounds of rhenium in its blades. 13 pounds of metal worth $30,000 to $60,000 in a single engine. And a plane has 2 engines. Thousands of jet engines are manufactured every year: passenger, cargo, military. Nearly all the rhenium mined in the world goes right there. Because of its rarity and high price, the industry is desperately trying to cut rhenium consumption. New generations of superalloys are being developed with lower content or using ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology lets manufacturers use rhenium more efficiently. Instead of a polycrystalline structure, the blade is grown as one massive crystal with no grain boundaries, the weak spots. This allows them to reduce rhenium content while maintaining performance. But the process is complex and expensive. Each blade is grown individually in specialized furnaces with extremely slow, controlled cooling. Recycling rhenium from spent blades is critically important. After thousands of hours of operation, blades wear out and get replaced. Old blades aren't thrown away. They're melted down. Rhenium and other valuable metals are extracted and used again. About 30% of rhenium comes from secondary recycling. That's more than most other metals simply because of its enormous value. The remaining 20% of rhenium goes into other applications. Catalysts in petroleum refining, platinum rhenium catalysts for reforming boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. Rhenium's strategic importance is massive. Countries without access to rhenium can't manufacture modern jet engines. This isn't just about civilian aviation, it's military too. Fighters, bombers, cruise missiles. The US, with its own molybdenum mines, secures its rhenium supply. Europe and Asia depend on imports, mostly from Chile and the US. China is aggressively ramping up rhenium production, developing their own molybdenum deposits. They get it. Without rhenium, you can't build a competitive aviation industry. Here's the thing. Rhenium was one of the last stable elements ever discovered. German chemists found it back in 1925 while analyzing platinum ore with spectral analysis. They named it after the Rhine, Rhenus in Latin. Before that, Mendeleev had predicted element number 75 would exist, but nobody could find it. It was just too incredibly rare. Every day, 5.5 million people ride the New York City subway, and the only thing standing between those 400-ton trains and complete disaster is just 2 inches of steel rail. These rails take an incredible beating. 300,000 wheel impacts every single day, temperatures swinging from -20 degrees Fahrenheit in winter to 140 degrees in summer, and somehow they never crack, never bend, never fail. So how do you actually make something that can handle that kind of punishment for 40 years straight? What's the difference between these subway rails and regular steel that would fall apart in weeks under the same conditions? Today, we're going inside one factory in Nebraska where these rails are made, and I'm going to walk you through the entire process from the moment raw materials arrive at the gate to the moment a finished rail gets installed in a New York City tunnel and a train rolls over it for the first time. The factory is in Norfolk, Nebraska, which is a small town of about 12,000 people, sitting in the middle of endless cornfields. And when you drive up to the Nucor steel mill, you see this massive industrial complex covering 3,000 acres, where every single New York City subway rail is manufactured. What's interesting about this place is that the entire process happens right here in one location. The iron ore arrives at the east gate, goes through all the different buildings and furnaces and machines, and finished rails leave from the west gate headed to New York. The raw materials show up on freight trains that pull in several times a week, and we're talking about 15,000 tons of iron ore in a single delivery coming from Minnesota's Iron Range, which is actually where America's entire rail steel industry got its start back in 1884. Along with the iron ore, you've got limestone coming from quarries a couple hundred miles west, and coke, which is basically purified coal that's been processed at extremely high temperatures. And all of these materials get unloaded and moved to different areas of the plant where the process begins. At the center of the whole facility, there's this massive blast furnace that stands 10 stories tall. And when you're standing next to it, you can feel the heat radiating off the steel and brick exterior even from 50 feet away. Inside that furnace, the temperature reaches 3,000 degrees Fahrenheit, which is hot enough to actually vaporize aluminum, and the way it works is pretty straightforward. Iron ore, limestone, and coke get loaded in from the top, while superheated air gets blasted up from the bottom at 600 miles per hour. What happens inside is that the incredible heat literally rips the iron atoms away from the rock, and all the impurities in the ore rise to the top as this liquid slag that gets skimmed off, and actually ends up being used for road construction. The pure molten iron collects at the bottom of the furnace, and you can see it through observation windows glowing this bright orange color as it flows out into these massive ladles that are about the size of a garbage truck. Overhead, cranes pick up these ladles, each one holding about 300 tons of liquid metal, and move them just 50 feet over to the next building where the real transformation into steel happens. In the building right next door, there's what's called a basic oxygen furnace, and this is where the molten pig iron from the blast furnace gets converted into actual steel that can be used for rails. The process is pretty intense. They blast pure oxygen into the liquid iron at supersonic speeds, and when that oxygen hits the carbon that's dissolved in the iron, it ignites instantly and creates these massive flames that shoot 40 feet up into the air, while the whole building shakes from the noise. The entire reaction takes exactly 18 minutes, not 17, not 19, but exactly 18. And what comes out at the end is steel with a carbon content of precisely 0.75%. That specific number is absolutely critical, because if there's too much carbon, the rail becomes brittle and will shatter when a train wheel hits it. But if there's too little carbon, the rail wears down way too fast, and you'd have to replace it every few months instead of every 40 years. The margin for error here is incredibly thin, like thinner than a human hair, because one small mistake at this stage ruins 300 tons of steel that has to be melted down and started over. From the oxygen furnace, the molten steel flows directly into the casting building next door, and this is where it starts taking on a solid form for the first time. The steel pours into these water-cooled molds, and what's fascinating is that the outside of the steel solidifies almost instantly when it touches the cold mold, while the inside stays completely liquid. The casting machine slowly pulls this steel through at about 3 inches per minute. And what comes out is this continuous glowing ribbon of solid steel that looks absolutely mesmerizing as it emerges from the machine. Automated saws cut this continuous ribbon into sections that are 39 feet long and weigh 12 tons each, and even after cutting, they're still glowing bright red at around 1,800 degrees Fahrenheit. These sections get picked up by robotic arms and transferred about 20 feet over to a line of reheating furnaces, where they need to be brought to exactly 2,200 degrees Fahrenheit before they can go to the rolling mill. The temperature control here is measured by sensors 50 times per second, because if the steel drops below 2,180 degrees, it won't shape properly in the rollers. But if it goes above 2,220 degrees, the internal grain structure starts to collapse. So you've only got a 40-degree window to work with in a furnace that's running at 2,000 degrees. The next building overhouses the rolling mill, which is where these thick, rectangular billets of steel get transformed into the actual shape of a rail. And when you see this process in person, it's pretty incredible. The glowing steel enters between two enormous steel cylinders that press down with 5,000 tons of force, and you can literally hear the metal screaming as it gets compressed and stretched. It sounds exactly like a jet engine taking off, and the whole floor vibrates under your feet. Each piece of steel has to pass through 22 different sets of rollers, and with each pass, it gets closer and closer to the final rail shape. In the first few passes, the billet gets flattened out and elongated. Then around the 5th pass, you start seeing the curved head of the rail forming where the train wheels will eventually ride. And by the 10th pass, the vertical web section is taking shape. And finally, after the 22nd pass, you've got the complete rail profile with the base that'll get bolted down to the railroad ties. The crazy thing is that this entire rail shape has to be accurate within 0.5 millimeters, which is literally half the thickness of a dime, across all 39 feet of glowing steel, because if it's off by even 1 millimeter, the whole thing becomes scrap metal, and 12 tons of work goes to waste. After the steel comes out of those final rollers, it's moving along at about 18 miles per hour and still glowing at 1,650 degrees Fahrenheit. And this next moment is probably the most critical 4 seconds in the entire process. Water jets blast the top surface of the rail at 800 pounds per square inch of pressure, and the temperature of that head section drops from 1,650 degrees down to 400 degrees in just 4 seconds flat. What this rapid cooling does is transform the molecular structure of the steel at the surface level. The head becomes extremely hard, almost like glass, while the web and base sections cool more slowly and stay flexible. This creates what's basically a hybrid material, where the top 2 inches are harder than a knife blade, so they can resist wear from 50 million wheel passes every year, but the bottom 4 inches remain flexible enough to absorb impacts without cracking. If the timing of this water cooling is off by even 2 seconds, the rail develops these microscopic fractures that you can't see with the naked eye, but will cause the rail to fail within months instead of lasting 40 years. Once the rails have cooled down, they go through cutting and drilling, where carbide-tipped saws cut them into their final lengths. 39 feet for sections that'll be installed on curves, and 78 feet for straight sections of track. Then, drilling machines create 38 precisely positioned holes along the base of each rail, and these holes have to be accurate within 0.1 inches, because each bolt that goes through them will be carrying 12 tons of lateral force every time a train goes around a curve. So if even one hole is misaligned, it creates a stress concentration point where the rail will eventually crack and potentially cause a derailment. And there's a very specific reason why the quality control that comes next is so incredibly strict. On August 28, 1991, it was a typical Wednesday morning rush hour at Union Square Station in Manhattan, and a southbound number 4 train was coming into the station when suddenly the train lurched violently and derailed. 5 people were killed, over 200 were injured, and the investigation revealed something terrifying. The rail had developed a microscopic internal crack during manufacturing, something so small it was invisible to the naked eye. But under the constant stress of trains passing over it day after day, that tiny crack had slowly grown until the rail finally gave way. That tragedy completely transformed how subway rails are made and tested. Today, after cutting and drilling, every single rail goes through what's basically the most thorough inspection process you can imagine in Building 6. Ultrasonic testing machines send sound waves through the entire length of steel to detect any internal cracks as small as 0.1 millimeters deep. Defects that are completely invisible to the human eye, but could be catastrophic. The rails also get checked by laser systems that measure straightness within 3 millimeters across the entire 39 feet. And surface scanners look for any pits, scratches, or rough spots on the head, where the train wheels will be riding. The rejection rate at this quality control stage is 11%, which means 1 out of every 9 rails that make it this far never leaves the factory. They get sent back to the blast furnace to be melted down and started over from scratch. It's expensive, it's time-consuming, but after what happened at Union Square, nobody in the industry is willing to take chances. Only absolutely perfect rails get loaded onto trucks at the west gate of the plant. The rails that pass inspection get loaded onto flatbed trucks for the 3-day journey to New York City, traveling east on Interstate 80 through Iowa and into Pennsylvania, then taking Interstate 78 through New Jersey, before finally going through the Lincoln Tunnel into Manhattan. They arrive at staging yards in Queens, where they sit and wait for their turn to be installed, because the actual installation work can only happen between 1 in the morning and 5 in the morning when the subway trains stop running and the crews have a 4-hour window to work. Installation teams use hydraulic lifters to carefully position each 2.4-ton rail section in these tunnels that are only 12 feet wide, and then they weld the rails together end to end using something called thermite welding, which is a chemical reaction that produces molten iron at 4,500 degrees Fahrenheit that flows into the gap between the 2 rail ends and fuses them into one continuous piece. After the welding is done, grinders come in and smooth everything down, until you can't even see where the joint was. And then workers bolt the rails to concrete ties every 21 inches, with each bolt being torqued to exactly 250 foot-pounds. Not too loose, or the rail will shift around, but not too tight either, or the concrete will crack. When the New York City subway first opened back in 1904, the rails they used would wear out and need replacing after just 3 years, and the trains could only safely travel at about 15 miles per hour through those tunnels. Today, more than a century later, trains run through those same tunnels at 55 miles per hour, and the rails last for 40 years before they need to be replaced. That journey from 3 years to 40 years wasn't just about better steel. It was about learning from tragedies like Union Square and building a system where quality and safety come before everything else. You've now seen how iron ore gets melted in a furnace at 3,000 degrees, how oxygen converts it into steel with exactly the right carbon content, how 5,000 tons of force shapes it into a rail, and why 11% of production gets rejected because only perfection is good enough to carry 5.5 million people safely through underground tunnels every single day. If you found this interesting, subscribe to see more of these deep dives into how the things around us actually get made. Thanks for watching. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle lubricating oils and heavy residues.
Medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point: gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture, a process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures.